Hey guys and welcome back. So I am a physics and maths teacher in London, and I thought today we would go through GCSE physics and specifically the electric circuits components. So the way these videos are going to work is I'm going to do a very brief summary of the overall topics and overall things you need to know, and then we're going to jump straight into exam questions because in my opinion the exam questions are quite different from the actual notes that you get taught in school. So again, we're just going to do a quick brief overview of exactly what you need to know, and then we're going to jump straight into exam questions to make sure we can ace the electric circuits part of your physics paper. So first things first, we have all of these different circuit diagram components that you do need to memorize. So how would I memorize them? In my opinion, the best way is, first of all, cross off the ones that are kind of obvious. I would say the open and closed switch, the lamp, voltmeter, ammeter, the variable resistor and regular resistor, battery and cell. I would say those are pretty obvious. So you only need to know 1, 2, 3, 4 and 5. I'd say those 5 can be a bit tricky. So what I'd recommend doing is using flashcards. And again, this is just something you need to memorize. You just need to know. With practice, it does help. But again, flashcards for those 5. If you want, you can include all of them. But again, I think some of these are pretty obvious that you have used enough that you probably already know what to do with them. But yeah, unfortunately, you do need to know how to recognize and also draw these in various circuits. The next thing I'd like to go through is basically the two equations that I think are really important, and they basically explain what electricity is. So electricity is simply the movement of charge. Okay, so it can be positive or negative. And that leads us to the very first equation, which is Q, the charge, is equal to the current times the time. Remember, current is literally just the movement of charge. That's all it is. And it tells you how many coulombs of charge, so how many units of charge, pass by a point each second. So if you'd like, you can think of it almost like the speed of the electricity in a sense. The other equation, which is really useful, is Ohm's law, which just says that the voltage, which essentially is how much energy each charge carrier has. So when we talk about electricity, our charge carriers are of course electrons. This voltage tells us how much energy each electron has. So if you'd like, you can think of it as how fast the electrons are moving in that sense as well. And R is the resistance. It simply says how difficult is it to pass through something. And I have a very nifty diagram to show you roughly how this looks. So an amp is a current, so it's just your charge carrier. So in this case, it's an electron. The volt is the energy that's pushing the electron around the circuit. And the ohm is making it difficult for the amp to get through. And how do you think of this? Well, think of it on like a micro level. I like to think of it as walking through a school corridor. So if I ask you to walk across your corridor at school and there's no students, it's easy, you can walk pretty quickly. But now let's say it's between lessons and you have hundreds of students walking in all directions. You travel far slower, right? You could say that the resistance has increased because it's more difficult for you to get from one side to the other. It's the same thing, but in this case, of course, we're talking about atoms. When we have our wires on a micro level, there are impurities. So these are atoms that stick out throughout the wire itself. So when an electron comes along, it bumps off these different impurities, which lead to it slowing down, which we measure as a resistance being higher. The more of these impurities there are, the greater the resistance. You do need to know the effect that different things have on resistance, such as temperature. Now, with temperature, as temperature increases, resistance increases. Now let's think about why this is the case. Well, what happens when you heat something up? Well, the particles inside of it start to vibrate, they start to move. So that means if these things start to all move now, I'm sure you can imagine that it's a lot harder to pass through because you're more likely to hit one because they're vibrating. So if I have just my fist here, you can go around it fairly easily. But if it starts to vibrate, you're much more likely to actually collide with it, which is measured as an increase in resistance. And there's a few others that you need to know as well. The last two that you really need to know about, and these are generic for all things, is one is length. As the length of the wire increases, so does the resistance. And if you think about it, again, if you imagine your corridor, I'm asking you to pass through it, you can go through it fairly quickly, but what if I doubled the length of the corridor? Well, it's going to take you longer to go through, and therefore the resistance looks like it's bigger. And the very last one is area. Now, this is the only one where it's an opposite relationship. If I make the area bigger, the resistance goes down. Well, once again, imagine if I made your corridor a lot wider. Well, now you're less likely to bump into impurities because everything spreads out more and thus the resistance is a lot lower. Now, of course, you have some special cases. So with a thermistor, which is a temperature dependent resistor, as temperature increases, resistance actually decreases. The reason for this is, remember what electricity is. It is electrons that are passing through a material. With a thermistor, as you heat up the material, more electrons become free, which means you have more electrons which are able to pass through the material, which means it appears, so what we measure is a decrease in resistance. And the very last one is a light dependent resistor, which is the same thing. As light intensity, I'm just going to call that Li, goes up, the resistance goes down, and it's for the same reason as the thermistor. As the light hits the object, hits the light dependent resistor, electrons are knocked free from their atoms and can therefore, there are more electrons free, which means it's a lot easier for electricity to pass through the material. Therefore, the resistance goes down. Again, with the resistance, it is a measured effect. So because the electrons are making it through the material more easily, we measure that as a reduction in the resistance. That's all it means. Resistance is just how difficult it is for an electron to pass through a material. That's it. And most of the time it's just dependent on what material you have. The very last thing you really need to know about is series and parallel circuits. Now, series is when there is only one loop. So what do I mean by this? Well, the loop thing just means that if I trace my finger around the wire, there's only one way I can go, right? I can only go along here. So if you imagine it as you're an electron, you're inside this wire, how many different paths do you have? Well, you have one path, you go all the way around. If there is only one path, it is a series circuit. However, if we have a look over here in the parallel circuit department, as I go along here, cool, I then get here, I have a choice. I can either go to the middle branch or I can go to the bottom branch. Because there's a choice of multiple paths, it is a parallel circuit. And you just need to know a few different facts about them. The first thing is, in series, the current is the same everywhere. So current is the same. So let's say I have 1 amp here, I'll have 1 amp here, and I'll have 1 amp here. Now, why is that? Well, if you remember what I said, the current is simply how many electrons pass a point each second. Well, if I've got a closed circuit like this, then the amount of electrons here should be the same as the amount of electrons here, same as the amount of electrons here. There's no difference because they're all going in one direction. Okay? Now, with parallel circuits, it's actually the opposite. Because remember, I said that when I get to this little junction here, I have a choice of going either along the middle or along the bottom. Which means the number of electrons actually splits, it reduces. So there will be half an amp here, half of them will go this way, and half of them will go this way. Because again, they have a choice. Some electrons will go this way, some will go down the bottom, which means the current will halve. At the end, because there's only one path, all of the electrons come back through this part over here, there will be 1 amp again. So again, all of the electrons have to go through this way, but then they split up. Then as they go around, they meet back up over here, and they pass back through, which means there is still the same number of electrons on either side, but in the middle, they will split up. Hopefully that makes sense. You can think of it in terms of a water hose as well. A series circuit is like having a single hose like that. Well, all of the water has to go along this way, so the water won't split. But if I then decide to branch off my hose pipe, you can imagine that the amount of water coming out of each end is smaller than the amount that's going in through here because it splits off. So you can think of it in multiple different ways if you'd like. What about the voltage? Well, here's where things get very interesting. If you remember, the voltage is the energy that I give each electron. Well, in this case, that energy has to be used in order to turn on each light bulb, right? So let's say I give each electron 2 volts of energy. Well, then it's going to spend 1 volt here, and it's going to spend 1 volt here, because it needs to use some of the energy to turn the light bulb on. So the voltage is actually split in series. Now, here's where things get a bit interesting. So the current is split for the reasons we said before, but the voltage, well, let's think about what happens to the voltage. Remember, The voltage has nothing to do with the number of electrons, it's to do with the amount of energy each electron has. Well, let's have a think. I'm again going to give each electron 2 volts. It comes along, and let's say the first electron goes along here. Well, it needs to use all of its energy, so it is able to give all 2 volts to the bulb here, because there's nothing else it needs to turn on. It only has one light bulb that it can turn on. Now the other electron goes down the bottom. Well, again, it has 2 volts that it can give up, and therefore, have a look. 2 volts are given to it, and there are 2 volts each here. The voltage is the same across branches. And this is because each electron can only go across one branch, which means it gives all of its energy to that one branch. That is a really quick overview of everything you need to know just for circuits. We are now going to start doing some exam questions to really hone those skills and apply what we've learned. So we have a really stereotypical question, okay? So it's going to have multiple parts and they progressively get more and more difficult. Bear in mind with your GCSE science, it's actually a relatively low number of marks you need to get in order to get a decent grade. It's usually around half marks. So keep that in mind, but let's try and get as many as humanly possible anyway. So complete the sentence, choose the answers from the box. The current through an ohmic conductor. An ohmic conductor is one that follows the relationship V equals IR, Ohm's law. The current is directly proportional to the what? Well, I is V over R, or you can just use this, but have a look at which side these are on. Well, it's proportional to the potential difference across the component. Now, there was one thing that I didn't mention about Ohm's law, and that there is a very specific condition, which is this last part of the question here, provided that the resistance remains constant. Now, resistance is not on here. So what did I say affects resistance? Temperature. This is a really, really important fact. If you get given an experiment question for this would be the reason why you always turn off the power supply in between taking readings on a circuit. It's because otherwise the thing will heat up, which will change the resistance, which means Ohm's law is no longer valid. Part B shows a current potential difference graph for a filament lamp. Explain how the resistance changes as the potential difference across it changes. The first thing I would do is, using Ohm's law, we have V equals IR, is work out what resistance actually is. So on a diagram like this, resistance is V over I. If I look at the gradient of this, it gives me I over V. So this is the really important thing, and it is quite tricky because the maths behind it is not the easiest. But resistance is voltage over current. The gradient of this decreasing does not mean the resistance is decreasing. This line here is actually the inverse of the resistance. It's actually 1 over R is I over V. So the gradient is actually 1 over R, which means as this curve kind of gets less steep, it means the resistance is increasing, not decreasing. That's the annoying thing about this kind of point. So you might be wondering, why on earth do we draw this? It's because the potential difference is the thing we control, not the current. The current is the dependent variable. So explain how it changes. So the first thing I would write is that as the potential difference increases, the resistance increases. There you go. That's 1 mark already. This was a 3-mark question, but now we need to say why. So 1 mark. I'm going to do this as bullet points because that's the best way to lay out your answers in science. Because as potential difference increases, current increases. 2nd mark, which leads to an increase in temperature and hence resistance. So the question is, why did I know I needed to put these 3 points? Because that is also a difficult thing. What if it just said describe the difference? Because it says explain, you need to give the actual reason for why the resistance changes. If it said describe how the resistance changes, it would probably be a 1 or 2 mark question, or describe how you can tell. 1 or 2 mark question where you just say it increases because the gradient decreases. You're describing. Explaining means you actually talk about the physics behind it. So as the potential difference increases, the resistance increases. Because as PD increases, current increases. An increase in current will increase temperature, which increases resistance. Many householders are replacing their filament lamps with LED lamps, which are more energy efficient. What does the term energy efficient mean? All you really need to write is less energy is wasted. And then if you want, you can actually give an example. So you can say, as heat energy. Because if you don't know how filaments work, I don't blame you. Most houses already have LEDs in them anyway. But essentially the way filaments work is they heat up a thin piece of wire. Because it gets hot, it means it gives off light. So by its nature, it's very, very energy inefficient, whereas LEDs just straight up convert electrical energy into light energy, which means they're a lot more efficient because they don't get as hot. A light-dependent resistor, LDR, is used to turn on an outside lamp when it gets dark. This is part of the circuit. So we have this bit which is all in series, then we have the parallel bit which goes to the actual lamp circuit which is outside. The light intensity decreases. What happens to the potential difference and the current across the LDR or through the LDR? Well, here's what I would do is think about the series of events. So the light intensity decreases. What does that have a direct impact on? It's a light dependent resistor. Well, I mentioned that as light intensity decreases, the resistance goes up. Now, I also, when I said that voltage in series is split, I didn't tell you how it's split. And the reason for this is because we have this beautiful question and part E, or is it F? One of the next two parts, which actually asks us to calculate it. And here is how it is. Here's how it is. It splits according to resistance. So the more resistance you have, the bigger the share of the voltage or current you get. So if I have a bigger resistance here, then I will get more of the voltage. If both of these were equal, then they would each get half the voltage. They'd each get 6 volts. However, if I change this to make it twice as big, then this needs to get twice the voltage this gets. So that is a ratio, right? 2 to 1. Which means if this gets 2,000 or 4,000 or whatever, the other would get 8,000 as an example. So if we said that this was 4,000 ohms, just to make the numbers easier, and this was 8,000 ohms, then this getting 4 volts means that this would get 8 volts. If you want, you can even remove the voltage from it entirely. If I say that this side over here gets, what would be a good one? Let's say this side gets 4 volts. Well, because this resistance was twice the other resistance, then it will get 8 volts. And if you notice, it still adds up to 12. So it depends on the resistance. So why am I saying this? Well, if the resistance of this increases, then you get a bigger share of the potential difference. So that means the potential difference increases. Now, when I mentioned what resistance really is, it's how difficult it is for electrons to pass through the material. So if it's more difficult for electrons to pass through this light-dependent resistor, then that means the current, how quickly they get through it, must decrease because it's harder for them to get through it. Again, think back to that hallway at school, right? It's harder, you move slower when there's a bunch of other people trying to get past you because our resistance is higher. What is the resistance of the LDR when the potential difference across it is 4 volts? Give a reason for your answer. Okay, so it says here that the LDR has a potential difference of 4 volts. And we need to work out what its resistance is. Well, remember what I said. That resistance will dictate how much of the voltage you get. So if this thing here gets 4 volts, the other resistor must get 8 volts. Now, because the voltage is twice as big, that means that this resistance is twice as big, which means the resistance here must be 1,000 ohms. Because again, it splits in proportion to how much resistance you have. If the voltage is twice as much here, then that means the resistance must also be twice as much here as well. That means, so how would I write that? Well, the first thing I'd write is the resistance must be 1,000 ohms. And the reason I would write something along the lines of, since the a resistor gets twice as much voltage, the resistance must be twice as much. Hence, 2000 divided by 2 is equal to 1000 ohms. Okay, already wrote for me. That's literally all I'd write. So again, that is the trickiest. Conceptually, it's a very tricky thing. So with a bit of practice, that should make sense. But if you're unsure, just ask me in the comments. I will explain it to you again. But again, the more resistance this has, if this has twice as much resistance, it gets twice as much voltage. If it has 5 times as much resistance, it gets 5 times as much voltage. So on and so forth. Calculate the current through the LDR when the resistance of the LDR is 5000 ohms. Okie dokie. 5000 ohms, yeah? 5, 1, 2, 3 ohms. Well, now we can work out how much voltage each of them gets. So the first thing you want to do is get your calculator out, like so. I'm going to work out how many times bigger this resistance is than this resistance. So if you like, it's kind of like scale factors in maths. So the resistance through the LDR is 2.5 times bigger than the resistance in the resistor. Okay, cool. That means it should get, whatever the voltage is here, it should be 2.5 times bigger on this side. Okay. So what we can do is we can basically make this a ratio. So it's 2.5 to 1. So that's 3.5 parts. So that means one part is worth 12 volts divided by 3.5. So 12 divided by 3.5 gives me 24/7, which means 2.5 parts is equal to that times 2.5, which is 60/7 volts. Perfect. So now we know that the resistance is 5000. The voltage is 60/7. If you remember, V is equal to IR, which means I is simply V divided by R. So you can put this all into your calculator. We can use the answer button for V, divided by 5, 1, 2, 3. And it says give your answer to 2 SF. So if I want to, alright, fine. Sometimes your calculator will give it as a decimal, sometimes it won't. If it gives it in standard form, then I'm hoping you know how to remedy that. But if not, you can change the settings in your calculator to make it give you a decimal. But this is actually pretty good practice. We have 1.7 times 10 to the minus 3. That is to 2SF. So you can leave it in standard form if you like. If not, that would be 0.0017 amps. Whichever way you want to write it is fine. Remember, it's not a maths test. They're not asking you to convert it, but if you want to, you're more than welcome to. So I'm going to do one last style of question. This was a part C one year, and the rest of it is about static electricity, which is I'm going to do in a separate video. But this was worth 5 marks. Pretty big. Now, I will point out that if you are coming from doing like the latent heat or specific heat capacity, they can use power in that as well, where you'd use P equals energy times energy over time to work stuff out. That, in my opinion, is going to be in a separate video rather than doing it in this video because it's not technically electricity. But this is the last major style of question they can give you. 5 marks, and it seems like they haven't given you enough information. So let's read through the question. A defibrillator transfers charge to regulate a person's heartbeat. Don't really care about what it looks like. When the defibrillator is in use, a PD of 4800 volts is applied across the person's chest, and a charge of 0.16 coulombs passes through the person's chest in 4 milliseconds. Calculate the resistance of the person's chest. So again, remember the 2 equations that I told you to remember. If in every calculation ever, you just write these out, you know what, let's also include P equals IV. Why not? If you write all of these equations out, you will be able to answer every single calculation ever. So we want the resistance. So to be honest, I can probably get rid of power. Why? Well, I don't care about power and I don't get given power. So let's just say that this one's not needed for now. Now, what is it asking me to work out? Resistance. So that's this equation. So I would have to do R equals V divided by I. What's the problem? Well, I have V. V is 4800. But I don't have current. Okay, let's look at the other information they give me. They give me a charge and they give me a time. Interesting. I equals Q over T. Because they've given me a charge and a time. This applies to every single exam you'll ever do, but there are two rules that examiners follow. One, the questions can't be impossible. You have to have enough information to do the question. Two, they will never give you information you don't need. That's how I knew that I was going to be using this information. Look, it's charge and it's time. What does that remind me of? Q equals IT. Oh, hang on. I don't know I, but I want I. So I can now work it out. That's the logic that's going through my head all of the time. In terms of the time, it's 4 milliseconds, which you can write as 0.004, or you can write as 4 times 10 to the minus 3 if you want to be a bit fancy. I'm not too fussed, so let's leave it as is. So let's go and do 0.16, whoops, that's not 16, over 0.004 gives me 40 amps. It's pretty big, actually. So my equation for resistance now becomes 4800 over 40. Of course, that is 0. Half it, 240. Half it again, 120. 120 ohms. That's 5 marks. 5 marks. That's almost an entire grade. Normally the grade boundaries are separated by about 7-8 marks. How long was that? Imagine a 5 marker in maths and compare it to a 5 marker here. It is so much shorter. I've done two things. I did this and then I did this. But that's it. That's all I had to do. There's no tricks about it. So, what's my advice with electricity? A, write out the 3 equations, always, and then use them to work out everything. If you're stuck, if you didn't know, okay, how am I meant to get current, try and use all of the equations to work stuff out. You'll find that only one equation will actually work. In which case, you know what to do. So say, okay, oh, can I work out power? Well, no, okay. Well, can I work out resistance straight away? No, okay. Here, oh, look, I can work out current. Try everything, and you will get there. Because it's only these 3 equations that you need. 3 equations. Which, by the way, are all on your formula sheet as well. The next thing is, if it's a circuit, imagine, this is going to sound a bit weird, imagine yourself as an electron. Imagine what's happening to it. It is logical, although it is difficult, and I completely sympathise. Electricity comes back in A-level physics, and A-level physics students find it the hardest there as well. It's not easy, but imagining yourself as an electron, as weird as that sounds, is the best way to actually picture what's happening. If there are any other questions that you guys want me to go through, I'd recommend posting them on the Discord. I will gather them all together and maybe make a video of the hardest possible electricity questions. But other than that, I'm probably going to move on to another topic depending on how well this video does. If it does really well, then I'm more inclined to continue with it. But other than that, I hope you have a wonderful day and I hope this was useful. I'll see you in the next one.